The film on the stairs coming in there. You get the rushing. Don't rush. Well, we can probably get started. Thanks for showing up and doing. It's like nasty out there. But anyway, so we got so Thursday, Jeff Schneider's coming from. He's the like vice president or something of Rumpke Recycling. Yeah, so he's like the top guy. So he runs the Cincinnati and the Columbus sites. And then on Tuesday after that, Harry Harms from the Cincinnati Reuse and Recycling Centers. So kind of like, I guess they bill themselves as like filling in the gap for things that can't be recycled by Rumpke. So anyway, so that's the stuff we're talking about today is more or less flexible packaging, which is the stuff that Rumpke doesn't take, that goes to the Cincinnati Recycle Center. Right, the week after that, I got an additive guy, this Amit Kulkarni's the vice president of Aviant, which used to be Poly1. It's like a polymer additive company in Cleveland. It's the main company that does that stuff. So it should be good. I mean, you should be able to tell us stuff. And then actually there's a lot of speakers, and Kelly Williams after that talking about that's like a specialty recyclable film company in town in Cincinnati. So, and then the week after that, Katie Beers from this is going to talk. And I might get a couple other speakers, you know, to fill in. But basically, I think a lot of times, like, I'm reading stuff from books, and I know some things, but I haven't worked in the industry. You know, it's basically, I think it's better to hear from people as much as we can, not as much as I can convince people to show up. So anyway, so today I wanted to go through this flexible packaging. Oh, the homework was really good. Like, all right, some of the homeworks were not as good as others, but some of them were like excellent. It's like whoever, if you got extra points, it's because I thought it was like really outstanding. Like really, people put a lot of time into the ones, like more than I thought they would. So it's great. I mean, it's good. It looked like people were getting stuff out of it, so it's pretty good. Anyway, so yeah, the grades. So a lot of the grades were over 100. You know, but one of the groups missed the question, so it was like -20, and that group, like if it was a person that didn't show up, you need to tell me who it was, and I'll put them in the group for people that don't show up. You know? Like a plan was like if someone doesn't show up, you park them down in the no show up group. So far, no one's in the no show up group. The only one there was a person that dropped like early on. So anyway, if there's people that aren't doing stuff, or you feel like, you know, just tell me the name and I'll just put them. It was stated at the beginning that was automatic, like, so there isn't any kind of guilt trip or anything on it. So in the end, you know, people, if in the past when I've done that, like the people actually like perform really well after they get to their own group. It's like they're only doing it, I think, because they feel like they can get away with it type thing. And then they end up getting the high grade on a lot of them. And so it's kind of a funny thing. So you really shouldn't, it's doing them a favor to do that. Anyway, so plastic packaging is like one of the main topics. So I wanted to, you know, I've broken it down into subject areas, and then we'll have a guy come in and talk about additives. I know you asked for that, and I didn't have a subject area for additives because I didn't exactly see how to make that into a subject area because it kind of is in everything. So, but we'll see what Amit says, you know, about additives. Maybe I'll put together maybe some notes on it. Anyway, packaging though, there's a lot. So I have, if you go to the web page under packaging, you go to packaging files. So we got this is a book, like the class book. If you go to chapter 4 of that, it's almost all about packaging. So the book has like 4 chapters. Chapter 3 is plastics, just like polymer science. And then chapter 4 is basically just packaging. So it's kind of like, I think one chapter is bioplastics. Wait, the name of it's Plastics in a Circular Economy, same as a class, but basically chapter 4 is kind of packaging. And then there's a book on plastics packaging, and then there's this flexible packaging. So it turns out, like, you talk about packaging, you have like milk jugs is kind of packaging, and milk jugs, most of that kind of solid packaging is recyclable. So it all could be recycled basically. But when you talk about flexible packaging, that's where the problem is. Like the EPA and the Department of Energy and I think the NSF, so every kind of funding agency has put a lot of money into flexible packaging as like finding a solution to it. So packaging kind of ends up being the same in our context, having the same meaning as flexible packaging, which means like films. And then the biggest problem is multi-layer films, which I'll talk about a little bit. So there's a book on that. This is a pretty good book, but it doesn't have a lot of good color pictures, but it kind of covers the entire subject. But it's not one document, it's like individual PDFs. So basically each chapter is a PDF. The MacArthur Foundation has been funding a lot in flexible packaging, like recycling the flexible packaging. And that's kind of like this is really the polymer processing people end of it. And this is kind of like the, whatever, there's a problem end of it. The other side kind of, this is the industrial side, this is a non-industrial side. And also they're funding government actions and things on flexible too. Right, so there's a lot of links here. I mean, you don't have to look at it all, but it's there if you want to look at it. And I've kind of summarized these things and some things from the internet and whatever I know, like into the slides here. So it's 101 slides, but more likely just pictures and things like this. So it isn't really. I think I can do 101 today, maybe, possibly, at a slow pace. But anyway, so the packaging. So you have some product and you want to have a good shelf life. So basically, transport properties are the big thing. So you want to, and the things that they measure for food are moisture, vapor, transmission rate, and oxygen permeability. So they have, like, if anybody went to the Lyondell tour, like they have a whole bunch of equipment just measuring that for all kinds of films and things. So that's the reason is that all that stuff is going to go into something like this, and basically not recyclable, unless, all right, not recyclable at Rumpke or any curbside recycling, but Cincinnati Reuse and Recycle Center takes some of the stuff, like pouches. So they take a lot of the stuff. So if there are places that take this, so they have to be kind of bundled. The nice thing about Cincinnati Reuse Recycling is that they guarantee that it's going to be recycled. Like it's 100% trustworthy. Versus there's a lot of, like Dow has the thing with the orange bags that's people seem to question. At least my wife questions whether it's really going to go someplace. And I guess there's news articles that talk about it. I guess I would trust Dow. I don't know. I don't have a reason not to trust them, but there's a Terra Pack is a company that's just doing recycling of multi-layer. They're also developing like materials that can be multi-use kind of packaging, flexible packaging. So it's a lot of activity in it, and there's kind of money to be made if you pick the right angle, or you can do volunteer work. So anyway, so the idea is like protect the product, and also hygiene. So flexible packaging is also in the medical field. It's like, so most of the medical pills and like IV bags and things are all within this category of like flexible plastic packaging. And they're all disposable, but they are not recyclable. So that stuff all has to be, all the medical things tend to be just have to be burned right after. And then the packaging also, a lot of it is the appearance. So like there's a lot of effort that's gone into like printing. So how do you print on a piece of polyethylene? Well, you have to like plasma treat it, and you're gonna have to be doing this at like 60 miles an hour film flying through, right? So you have to plasma treat and then print. And it's gonna have to come out and look like so perfect. Then you're gonna make like millions of these, right? So basically, there's a lot to the packaging business. A lot of effort's gone into like figuring out how to solve these problems, like so your cornflakes don't get soggy type thing. So the good thing about flexible packaging is it doesn't weigh anything. You're using like almost no material. The thickness of this is like a quarter of a human hair thickness. So the amount of material, so yeah, it's a solid waste problem. Basically, the amount of material by weight is like nothing. Right. So if you replace this with glass or aluminum or paper, right, it's not going to perform the job as well. So the food's going to spoil. So you're going to throw away the food. The shipping is going to cost a lot more to move it around. And then you end up with a lot more massive waste from it that can be recycled for glass and aluminum, but basically there's a lot more of it. Right. So at some point you have to do kind of a life cycle analysis in these things and figure out if throwing this thing away, even though it feels bad, is actually better for the world than using the alternatives. Because you're not going to not eat the whatever this is, munchies, but you're going to get the munchies in some kind of package. And so it's important to kind of look at the big picture of it and try to back off from this is plastic, it's bad attitude, I mean, to me, that's a big problem with it. Like if you're just blinded by that, you're gonna actually hurt things. So that's at least the argument from the flexible packaging industry, which I'm kind of siding with. But anyway, so minimal usage, and then also like for shipping, these things can just stack up and take no space, right? So if you're shipping it in trucks or whatever, you can fill the truck with these little baggy things full of munchies, versus if they're in a box, it's going to take up a lot more space. Like candy and little paper boxes can take up more space than a flexible packaging. That means more trucks, more CO2 from the trucks, right? So, and more storage areas. So everything adds up. Like if you can make things smaller, it's better. And you can tune. So glass and aluminum have pretty good barrier properties overall, like they compared to plastic, right? But in this case, you can design these materials in multi-layers to have like such good transport properties and less material, right? So anyway, tuning of the product is in comparison with the other alternatives. Well, paper has no good transport at all. But basically these things can be tuned to have same transport basically as glass and aluminum, but they have no mass to them. So it's a nice thing. So anyway, this is kind of some recycling plant. This is, if you tour Rumpke, you'll see something pretty close to this. I don't think their stuff is green, but basically conveyor belts carrying like flexible packaging and various kinds of separation devices. I'll show you some later to separate the different components that are in the stream, the metallized parts and non-metallized. So anyway, that's kind of the garbage issue. That's it. I don't know if these things are sensationalized or what. It's hard to tell, but stomach of a whale in 2017 had these bags in it. That's flexible packaging, on the bad side of it. Anyway, so this is the kind of the tech end. Like you get your potato chips in the bag, it's got at least 5 layers to it. It's just even though the thickness of this is 15 micron, so like a tenth, like a fifth of a hair, human hair, right? But it's got like maybe up to 10 layers in it, right? And it keeps the chips like totally whatever, and it's proofed out so it keeps them from breaking. So it's been all these things have been designed over the years, right? So anyway, so it's going to have some kind of strong layer, so it doesn't. I mean, that makes it hard to open. Maybe basically it's tough to rip it, so it doesn't break open. It's got glue holding the layers together. Each of these is like a micron or 5 micron maybe each. So really thin. There's this is a vanillidine chloride, so it's like PVC, but it's got an extra chlorine on it. So 2 chlorines per monomer. So that anything that's chlorinated has a good barrier. Anything with a hydroxyl group on it has a good barrier. So you want to have these kind of thin layers of these, or you can put aluminum in, like you can do aluminum coating in the process, like in the process stream. Right, so it's all that is done like right on the film line is making the films to go into the bags, and the printing's done there too. So you have like, you can have like a inkjet printer printing this outside, and then it puts an outer layer to protect it of like polyethylene. Again, it's like 2 microns thick or something. So like you don't even notice it's there. Or it can make it shiny with different grades of polyolefins. So the tie layers are basically glues holding the other layers together, so it doesn't separate apart. So it's an engineered material, like it's not so simple, right? But because of that, like how do you recycle that thing? Well, I mean, there's people that are doing the recycling. I mean, there's a lot to it. Like, in other words, you're going to have to separate the aluminized material from the other materials. And there's ways to do that, right? So there's all technology. These are all run on conveyor belt speeds, like high-speed conveyor belts. So basically the separation of the different components can be done. I mean, different types of film, multi-layer films can be done. And anyway, so these are some of the kind of examples, like a grocery bag can be a 3-layer film, like can have high density, and the properties that touch the food are like linear low density, tuned branch polymer, low molecular weights and makes it soft, and then high density for strength in the middle. And then cereal liners are going to have a alcohol, ethylene vinyl alcohol, so it's polyethylene copolymerized with vinyl alcohol. So just an OH group on the side of polyethylene, which would be a barrier layer for moisture transmission. Then like liquid paste packaging, these are all going to have some kind of aluminized layer in it to protect for transport again, like prevent the oxygen going through, and also to block light from getting into it, the UV light to degrade the whatever's inside of it. Same thing, like aluminum, this got tie layers and a PET on the outside for juice boxes, basically. And you can include a paper layer in this too. Like the juice box is going to have like a cardboard going through, and it's going to have multiple layers of plastic and aluminum. So it's the same line, you can just feed paper into it, right? So basically, paper is just another thing that's fed into the multi-layer packaging. In fact, things like a milk carton. So you have a milk jug, you have a milk carton, right? The milk carton's paper. You say it's better because it's paper, but there's actually more polyethylene in the milk carton than there is in the milk jug. It's basically, it's paper, yes, but it's like soaked in polyethylene. You know, so it's actually just the paper is just like a fiber composite supporting the polyethylene, right? So it gets to be a little weird, like you're talking about which is a better product to use. You know, so it's kind of debatable. You know, I think Rumpke's taken the milk cartons now. They take milk jugs. They take both. Originally, you had to pull the polyethylene cap off, but I think they've stopped doing that now. I guess we can ask Jeff when he comes, but anyway, you can see that they're engineered materials. These are simple, like a ketchup bottle, like Ryan mentioned, can be like 9 layers. So basically, these are fairly simple operations to do a 3 or 4 layer film. Right? This is a picture of like kind of how these things are made. Anyway, that's the machine that does it. So they had one of these at Lyondell. So we saw, I don't know, there were only 5 people, I think, that went, but basically you're going to have like a bunch of extruders. Each one's kind of like 3 people size. And each one's going to have a hopper with pellets going into it. And they're going to extrude into this multi-layered die. I think there's a picture of it here, something like this. So they're extruding into something like this. Each one's kind of going down and ends up, there could be, the middle layer might not be a polymer, it might be paper. You know, so you could have paper going into it. Anyway, so that all the layers come together like that into this area. Then you're going to have like there'll be multiple steps of coating it. So you have like a plasma to kind of activate the surface so that ink can stick to it, right? And then basically there could be different kinds of printers here that print onto it. So it can be a inkjet printer, high speed, high quality inkjet printer, so that you can make packaging quality materials. Then you go down and it's got, this could happen before or after, is this kind of orientation thing. So you have machine direction orientation, it's like pulling downstream as you're flowing it, and transverse direction is this kind of thing where it's getting wider, right? So the biaxially oriented polypropylene, which is BOPP, it's like the standard for film, for multi-layer film stuff. So basically, there's a lot of science that went into like how you do these orientations for these films from an extruded film like that. I mean, so how does that affect the transport properties? Or what temperature do you do it? What's the draw ratio and all this business? So you end up with a film that comes out onto a roller. So that could be that you could ship as a product, and that can go to a plant that's kind of maybe print the label onto it. So you could have a different kind of coating operation. This could feed into another machine. It's going to plasma treat the surface. And then it's going to start putting on, you could put an aluminum layer in that step, or you could do it here. And you could print onto that to make the packaging you want. That's going to go into a roller. Then that roller is going to go to another place. It's going to make bags like where they actually package the potato chips. So it'll be a potato chip factory next, and then inside of it, they buy these rolls already printed with stuff on it. That just feeds into it, and then it's going to crimp it. So the inside layer of this is going to be low density, linear low density, or something with low melting, or metallocene polyethylene. It's got a low melting point, so it can seal. So it's like a sealing layer. Well, that's PE. So there's going to be a sealing layer to make it stick together. The big problem is that the bags rip apart. So this is a biaxially oriented polypropylene multi-layer film, just showing like a 3-layer film or 5-layer, just showing kind of the thicknesses that you're dealing with. So it's the overall thing is going to be like 50 micron. So, oh, and you're going to end up with these things, right? So, and this just showing like the seal strength. It's like, so they do the test. Like if you went to the Lyndale, they had all machines to test like ripping films apart and things. Like they have a whole floor of these things to do weird ripping tests, moisture vapor test, and like lifetime analysis over 100 years. Is a potato chip still crunchy, whatever. So there's machines that do all these testing. All right, this is a 5-layer, 3-layer. How does the seal strength go? The 5-layer has better strength than the 3. And it's kind of meaningless, but basically that's the kind of thing that's going into these things, like engineering the packaging. And it's just a slide showing different end uses, kind of what the film. So these, like hair is 50 micron. If it's a thick hair, it's like 80 micron. You know, depending on mesh. So basically, these are all like hair thickness products that they end up with. But and then these are the numbers that trying to get oxygen transmission rate, water vapor transmission rate. That's like the spec of these films, so that you know it's going to be good enough for Pop-Tarts. Okay. And so anyway, and the meat's got its special issues. Like, so it's been, I have a plot somewhere, it's like oil content of the food. So it's going to have a high oil. It turns out the transmission of oil, it makes it like you have to have special films to deal with oil. Oil's a big problem because it's kind of soluble in the polymer. So it can kind of leaching becomes a problem with the oily things like meat. This is just a picture of that ethylene vinyl alcohol. This is a barrier. So it's just got an OH on a polyethylene. This alone is PVA, just kind of like the Japanese cotton, I guess, because Japan didn't have cotton or something, and somehow they use a lot more EVA in Japan to make clothing. Like they swap it out for cotton, basically. I mean, I think somehow this sourcing of cotton, I guess cotton comes from the US. EVA didn't get anywhere. It's just a petrochemical byproduct. If you add more EVA, you get lower oxygen transmission. So the EVA content of the oxygen content of the EVA goes up as you go to the left on this, and you get better barrier, better oxygen OTR. So that's just showing. So for these multi-layer films, it's a whole industry in itself, just saying, predicting what kind of multi-layer film do you need for your whatever kind of potato chip you're packaging. So there's computer programs that predict like the transport rate through these multi-layers and kind of how you could tune that to get whatever you want, however long life you want for your food. Right, this is one of the commercial packages to do that, Migra Test Light. That just shows like what, when you go into it, how it works or something. Then, so these are like the numbers they look for. So if you want like sensitive food, you need high oxygen, you need low, all right, so lower is better in this plot. So the highest stringency of the material is going to be like for electronics, like OLED displays need this kind of transmission. I don't know, LCD needs that, and food needs something a little bit less, but it's still a significant thing. And this shows a map on the same unit. So this is meter squared per decabar, I guess. Not sure exactly on that yet. No bar, but I don't know D bar. And then this is meter squared per D. D is something else. But anyway, so on this plot, it's going gram meter squared D 10 to the 2, 10 to the minus 6 for WBTR. 10 to the 2 to 10 to the minus 6. So it's kind of like in here, right? I should have marked this. On this one, it's 10 to the 2 to 10 to the minus 6. Has the same range, but it's centimeter cube meter squared D bar. So that's this unit. So it's 10 to the minus 2 to 10 to the 6. So it's kind of like the same ranges between these two. I should put those two on the same plot. But anyway, so basically the kind of materials you're looking for is at the low end of this, even lower than this. So that's polyvinylidene chloride. It's like PVC with 2 chlorines. This is ethylene vinyl alcohol, so that barrier material. So those are the ideal materials, and other things like polystyrene are as good. They aren't good enough for this barrier layer thing. So then you can do things like you can add, well, you can coat. So you can coat the surface with silica, coat it with alumina, coat it with aluminum. Right, so you can do a coating, and that's going to significantly improve the barrier. This is the barrier improvement factor. So if you start with a barrier of like 1, then you're going to get a barrier of 100. Like if you put silica, coat it with silica. So for oxygen and moisture. So this is just a process that you can do with the films, just coating this onto the films and during the manufacture. This is the permeability versus thickness of aluminum coating. Basically a small amount. So this is in nanometers. So a 20 nanometer to 200 angstrom, 0.2 micron, let's see, 0.02 micron aluminum film can kill almost all your oxygen permeability. So it's like nothing, right? It's just a sputter coat of aluminum, like a very thin one. And then it doesn't do much if you put more aluminum. This is before and after coating. It's like before is this and after is this. So it doesn't have it loses, so that the coating is all the barrier at that point. So that's why people put aluminum. That's why everything has this like shiny aluminum films. Anyway, so then you can dump in clay. So mica's like mica martmorillonite is a kind of clay. Basically, you can exfoliate the clay. Kaolinite is a clay. So these are like dirt, basically. So you can throw dirt into it, clay dirt, and mica's a mineral. It's like dirt, kind of person mineral. But you can add that in, and you can get. So basically, these are all sheet materials. You're going to increase the diffusion pathway, and crystallizing the polyethylene has the same effect because they have sheet crystals. So you're going to have the similar. So if you have biaxially oriented polypropylene, these are polymer crystals, and the polymer amorphous have the same property of improving the barrier. But with these sheet clays, like it actually, I mean, they're better, right? Because they're going to have this improvement factor of like 10 or something. So it's better than the film that it started with. Right, so there's a lot of kind of science that goes into this. This is the kind of thing like these are fragrances like limonene and citronello. Those are fragrances. Methanol, menthol. Sorry, that's also a kind of a fragrance flavor. So these are all things that stink. So basically, this is the how much of the stink permeates through the film as a function of time for these different things. They're showing that the depending on what you have, the transport is going to be different for different things. Right, this hexanol has a low transport, and the diphenyl oxide has a high transport through a 16 micron biaxially oriented polypropylene film. Right, so it's kind of like depends on what's in there, and if it's meat, it's a rapid transport. Like meat is a problem, and oily things are a problem. So this kind of making these films. This is like fat content, molecular weight of the stuff that you're shoving through. It's like what's the molecular weight of these things. So the molecular weight's down here, then the film thickness. So you have like 3 film thicknesses, top, middle, bottom. This is the migration rate of whatever the stuff is, which has fat in it. And the stuff with the highest fat content has the highest migration rate. And it's kind of what you think. The thinner the film has higher migration. I mean, it's kind of like what you think, I guess. So basically, people are studying that. So these are just like some of the things that we're talking about. Is like bags, twist things for candy. These are all the waste problem things, right? So, multi-layer pouch things for juice or whatever, or applesauce, whatever it is. And then labels, right? So labels, if the labels are the same, labels can be the same material as a base bottle. So you can have like polypropylene label on a polypropylene bottle or a PET label on a PET bottle. But basically, if they mix, then that's a problem that has to be removed on the recycle stream, right? So that these are all issues that you have to deal with. It's like, and how do you identify that when it's coming down a stream, right? So these things could be regulated, but they aren't. Like you could say, like you have to keep the same material for the label, but they aren't. So basically, anyway, that's an issue. And then this is how it affects. So this kind of a map of like, so you have a PET bottle with the label that's made of PVC, and like what's the consequence in terms of different kinds of sorting steps, like how it's going to impact it. Anyway, people have looked at this extensively. You can see there's a myriad of combinations of things that you can run into, but every one of them has to be dealt with separately, right? So you can imagine you got a conveyor belt with garbage. We'll see, hopefully you'll talk a little bit about the recycling on Thursday. Stuff's flying by, and like these are the decisions that something has to make to figure out how to separate things with a label on it, right? So it's complicated. It's a whole, you can see there's a lot of jobs in this in the future. And it's kind of like someone has to figure this all out or regulate it. You know, there's jobs in the government to figure out how to regulate it. So the stuff's going to come in, you collect it, that's your street collection or whatever you have. Then it's going to be sorting, and then it's going to be shredding. For in films, you're going to be shredding, cleaning, and second sorting because the films will break apart. And then somehow it's going to be made into some package. It's going to go to recycling. Right. So this is what a shredder looks like. This is what washing looks like, I guess. I haven't actually seen washing, but this is in this book. This is in there's a book on flexible packaging. This is just shows that for washing. And I couldn't find any better picture of washing. So it looks like, I guess that's what it looks like. So and then the separations of once you shred it and wash it, once you wash it and shred it, then you're going to look at like, this is a classic separation, like polypropylene falls and high density PE and low density floats. So you can separate the two major, 80% of the waste is going to be polypropylene polyethylene. If you shred it, you can just separate it in water, just dump it into water. There's a floating part and a sinking part. And then you can hybridize that thing. You can put in a ferrofluid, which is iron oxide, just in water and alcohol. Here it's in water. So it's a suspension with some kind of surfactant on it, maybe. And then basically when you put that in a magnet, the iron particles like dance kind of. So you can, by using magnetic field, you can adjust the density of the liquid up and down. And you can do this as a continuous stream through with your plastic, shredded plastic going in. You can tune the density so that with a splitter down here, you can separate basically anything you want. It's kind of a cool thing if it works. I haven't seen a video of this running, but basically this seems to be in all the books about this magnetic density separator. They might have it at but this is a electrostatic separator. So some things charge plus, some things charge minus. If once you shred it up, they're electrostatic. Then froth flotation. I don't know, you can imagine what that is, I guess. This is a standard thing you see at Rumpke if you go out there. So they have a blower. They use this to separate cardboard from everything else at the start. You know, so you have everything coming in, cardboard is part of it. They have a blower, cardboard flies up and goes onto another conveyor belt. The other stuff falls down. It's basically that's paper separation, but you can use it for plastic too, different kinds that are, it's kind of a density separation. It's kind of an aerodynamic separation, I guess, but I mean, there's like you can do separations with a hydro cyclone thing. Heavier things go to the outside and fall down. And then the lighter things go up through the middle. So those are some of the separation things. Hopefully we'll talk about those when it comes, you know. Then there's things that don't recycle, like the 6-pack rings, I guess. I'm not sure why they don't recycle, but they don't recycle. Straps and tapes, they don't, no one recycles those. But again, like all the stuff that doesn't recycle at Rumpke, Cincinnati Reuse and Recycle Center will take. So if you're willing to package it up and drive to Price Hill, like you can, they'll just take it there. So it's kind of nice. It's like, I mean, you need some storage area to keep your garbage, like long term, right? So there's downsides to that, but basically that can work. And then there's these kind of industrial bag things. So basically all the industrial plastic is recycled. Everything is like this that would be used at a farm or something. It's almost all recycled now. It's like that stuff doesn't go to a waste stream because they'd have to pay to haul it away, and they actually get paid for this stuff to give it back. So a lot of the industrial packaging is just being done. Now, this just shows different printing methods. Like this is the flexographic method. There's 3 kinds: flexographic, rotograver, which is like the old style where you have a bath of ink and it prints onto it, and then digital is basically inkjet. So these are all used to make like labels in line at high speed. Like these are all done like so fast you wouldn't believe it's flying through. So they're making millions of these things, like I don't know, in a day or whatever. But so that should have been earlier, I'd say. This is also like kind of just applications. So they keep mentioning these detergent pouches, like these things. Anyway, these are made of polyvinyl alcohol, the same thing the Japanese used to make like cotton kind of, and it dissolves in water. So I'm not sure exactly how that's a plastic waste because it seems to disappear. It is a packaging, it's a flexible packaging, but it's kind of a packaging that solves its own problem, I guess, except somewhere downstream, the polyvinyl alcohol goes into the water. I'm not sure if it's ever removed, so it ends up maybe in the Ohio River. I'm not sure what happens to the PVOH. The P&G people probably know. Do you know anything about PVOH? Like what happens to it? No one knows. It just goes away. I mean, it's going to be a polymer. It's still a polymer when it goes into the water, you know. So at some point it could come out. Fish definitely eat it. I mean, I guess sometime they'll do a test and everyone will have PVOH in their bladders. Anyway, this is just showing, this is supposedly going through like the different, like food and beverage, cleaning products, medical personnel, just showing like these pills. What do they call it? Blister package for pills is all like waste plastic with aluminum. Right? It's a mixed multi-layer film packaging. Basically, it's just thrown out, not recyclable. Maybe Cincinnati Waste Center takes, and these things are thrown out. actually, they have to be incinerated because it's medical waste, right? So I don't know. I mean, they don't, all right, if you compare this with a glass bottle, there's a lot of advantages to this. One thing is clean, like it's sterile, and so it'll remain sterile. But another thing, the glass bottle, so if you're gonna take the liquid out of the glass bottle, like blood or something, you have to put air back in, because otherwise you make a vacuum. And the air has to be clean air. So there's an issue of contamination of the blood or the saline or whatever you're getting, right, as it feeds to you. That's kind of an issue, right? So this thing, the bag actually squeezes down, so there's no air needed, like it's just gonna flow out. So it's technologically, it looks like garbage. This is a huge improvement over what was there before. Like you can imagine people were getting sepsis and things from the bags that were being used at the hospital, right? So I mean, so yeah, it's a solid waste problem and we burn it, so it's a carbon dioxide problem, but some things might be worth it, I guess, you know, depends. Okay, this TerraCycle is a big player in it. They have a web page, go to it. And it basically, let me just say, I think I have to do something else, like Microsoft has identified a potential, check yes or enable all hyperlinks file. That's good. Did that work? Because after I'm not sure this is worth it. It's just like their web page. But that should work. Yes. So there, yeah, you can go to this website. This is a pay for use thing, so you have to. So a lot of these are like, so there's business involved here. Like you could make a company recycling all this. See, it's all this stuff that can't be recycled. So they'll take all that stuff. Right then. So my wife says, like, well, you can't trust them because who knows what they're doing with it. They're taking money to take the stuff from you. They could just burn it, right? It's like the New Jersey problem, like you see the truck going down the road with a leak coming out. That's their hazardous waste disposal system, you know? It's like, so you can never tell, but this TerraCycle is supposed to be like reliable. They're partnering with all the companies, right? So they even have like TerraCycle loop where the company will make a packaging that you can reuse. Does P&G have that? I think they're part of this. Where you have packaging that you buy that you can refill kind of somehow at the store and like.
They are working on it, but it's being launched in Europe right now because consumers in America don't really like it.
Yeah, well, anyway, there's other companies that are doing it.
But like they're trying.
Yeah.
But like I don't think that is coming here. I think they're gonna figure it out in Europe first and then.
Well, that's because they have to in Europe. You read the regulations by 2025, which is next year, they have to do it. So they're only going to do it probably because they invented the biodegradable diaper and they threw the technology away. So they could have been making biodegradable diapers right now. So basically, I think without someone saying like you have to do it, I doubt that it's going to happen.
That's about like this thing. How they like invented. It's safe. I don't know what's gonna happen with it, but like it was, they use it to keep trees alive.
Oh, that sounds good.
Like it like expands.
Oh, well, it's the same stuff, right? It's just the acrylate super absorbent. Yeah, that could make trees survive.
Expands, and eventually it like releases water back.
Yeah, that's your super absorbent. So they're taking old diapers and shaking them in Africa. I mean, it's okay. It's already used in agriculture. Like they already put it into soil. Like the farmers use it here. Keeps the water in the soil.
Yeah.
Well, it's a big waste problem, but it's also like if you had kids, like it's a huge, like, I mean, dealing with cloth diapers is a huge mess. I mean, there's companies that do it, but it's kind of a nightmare.
They do save a lot of like premature babies because they make them premature babies. I mean, that's
Yeah.
not helping with the waste of home, but at least.
Yeah. Yeah, no, I'm not really arguing against it exactly, because I've lived through it, so I know that like you couldn't live without those things. But basically, it is a waste problem. And if I picture that they had already invented and invested in a process that would make them completely biodegradable. Except your super absorbent would have gone into the soil, but so why not, like, then they just threw that away. I think they figured out there was no, just exactly what you said, oh, there's no market for it. But if you had a regulation that said, I think they did it because they were afraid there was gonna be a regulation that said you have to. And like they would have to switch over right away. And someone else, like the guys in Wisconsin, would have done it before they did it or something, you know, so. So I mean, anyway, they had it, but they threw it away. It's kind of ridiculous in a sense, you know.
Dishwasher closet there or Tide pods.
Yeah.
Tide just released though, and it's literally like a fabric square. And you just put the fabric square in there, so there's like no plastic, there's no water.
Okay,
I have some, I can bring them in.
yeah, good. So so you reuse it. So, yeah,
No, you don't reuse it, but it's like basically all like the surfactants, the soap, or like, they basically spin.
Oh, I
it
see.
into
It's in the
fibers.
cloth. It's in the
Yeah.
cloth. Yeah, I have seen that.
And then,
They could bring it in. We need to look at it, I guess. I haven't used it or anything. So you end up with a fabric that's a waste after, though.
yeah, yeah. they have
But it's
like-
easy to use, like, I guess
Yeah,
that's
you
the
literally
idea.
just drop it in, they have like this technology, they basically like spin, like surfactants into the fibers. And then
Oh,
it
I
goes
see.
down, and then
Oh.
so it's like, like almost like a pad or a cloth.
I see, yeah.
And so like, if you were to use that for detergents, it's just like, literally like the soap itself into like some sort of cloth.
I see.
Put it in, it dissolves, it does its thing,
Oh,
but
so
they
this-
also expanded that to like peel away, face melts.
Uh-huh.
Like that, like you literally just put the face melt on your hand, put it under water, and then like it basically soaks, and then like you rub your hands together, and then surfaction activates, so
Uh-huh.
they're like trying to like, they have that too with like a hair product, where it's like shampoo and conditioner, once again, you just put it under water, and then there's no, I mean, other than the packaging itself,
Uh-huh.
there's no waste. But like the plastics coming.
Yeah, it'd be good to get someone to come in and talk about that stuff. The guy, or I'm almost there, like I got the guy to say. Anyway, I'm almost there, and I have a guy that retired from P&G that could talk about the bad side of things. Which would be good. That would be more, no, it'd be a lot more interesting because he isn't constrained by like, I get fired if I say something bad. You know? Yeah, I mean, anybody would be good that could know something about it and could just tell them the truth would be nice, you know? Like unabashed truth about the bad side and the good side, like, you know what I mean, like, cause you can't get that, people are constrained, like they have a job, they can't say. I mean, maybe they'll say a little bit, but not everything, so.
The craziest thing I've heard is that they think that it's, which I can. Like consumers like always are like, we want something that's compostable, like we want compostable this, we want recyclable this, and then they don't do it themselves, or like they don't
Right.
want to like. Use it, or they're like, oh, I want this ingredient in my product, but like that ingredient, one, does nothing more, or is like more harmful.
Yeah,
So
I mean, the
it's like-
diaper is a good example, like the cloth, it's there, it's available, but man, it's a pain in the neck to use, you know? I mean, it's a mess, you know? Like the other thing, you just toss away, it's gone, that's it. So, I mean. I don't know, I know what I did, but. so, but it's like, it's weird that they had the solution and they just tossed it, you know? I mean, anyway. It might be hard to get, it's hard to get anyone from the company to say anything like that. So let's see if I can get that here. See if I can figure out. That's weird. There, that's good. This is our spec right there. All right, so then there's this other company doing the same thing as TerraPack. I'm pretty sure Terra Cycles with P&G. They have some links with them. Garner's doing the same. They also have a web page. Then the Cincinnati reuse whatever stuff, which is like they're going to come and talk on Tuesday, but it's like this is their should go to their web page. But so you can volunteer there. They basically take their theme is like we take anything, we take everything Rumpke takes and we take everything else too. Like we take whatever's left over. Right, so you can see flexible film. Flexible packaging is like right there on the ball. This thing doesn't want to go there, but oh, because they have a video that you watch. I'm not sure if she's the person is gonna show up, but. Anyway, they're asking for money because it's not, they're not making money off it. So it's kind of like those other companies like TerraCycle. So someone had the idea, like, this is a problem, I'm gonna solve it, give me money and I'll fix it. And then Rumpke is also in the business of, we'll take money from the city and we'll fix it partly. And then they're also in the business of like, we'll sell the stuff and make money from it. So there's money being made from it, but there's also this other end of it, like, it's a problem, we're gonna fix it, we don't need money, So, and then I actually cover the things that no one else is going to do. So they have a whole, they have like a factory kind of building and a Price Hill, I think. And it's on the other side of the railroad tracks. So I know that's really bad button to push. Move like this. Then I'm not sure how that got inserted here. Let's see, it's like medical, then it went to this stuff. There's just like what it looks like. So this construction stuff, this stuff's all recycled. Like all this stuff about by the bricks, it has plastic wrapped around it. That's like, I think it's like 90% recycling of that stuff. So they can just feed it and like get the same thing back basically. And then e-commerce is a problem. Like for a while, so Rumpke won't take this, but you can give it to Kroger. That's another place to recycle flexible packaging, but only certain types, like clean polyethylene packaging they take, which is like these things. And then these, like the Cincinnati Recycle Center will take those things too. So let's see, 50, it was 101 slides in here, so there must be a lot more stuff. This is just saying, I already said that. And this is kind of argument for flexible packaging. Like I already said that basically. Right? And then this is a problem with the recycling business. And this is just showing some things of recycling. Like this is these are kind of grinders to grind up. Incoming is just plastic bags and outgoing it's like shreds of plastic bags. So it's all these things like labels and multi-layer films and printing. These are all problems because it makes a recycling area. So then what's they have in there? I got these from different sources, so they kind of repeat some of the stuff, right? The Dow thing is this, it's in here, this is an EU thing. But they see it's a moving target and flex, like they said 2025, and now they changed it to 2030. But then, and actually it's like 10 years later. So everything keeps getting kicked down the road, these things. This is this Dow, the Hefty is the Dow. They have, so you can sign up for this. You can just go to this web page, request a starter kit, they send you a box of stuff, orange bags, and then the orange bags supposedly are picked up in Cincinnati. This is all over the country, but basically Cincinnati is one of the sites that's doing it. And it's basically you can put in flexible packaging, basically everything that didn't go into Rumpke can go into this thing. So if you take your recycle and put it in a garbage bag and then put it in the recycle bin, right? So that the garbage bag is flexible packaging and they don't take that. So no matter what you put in the garbage bag, it all gets tossed into the landfill. It's kind of like people need to, a lot of it is like you need to know the rules about what's going on. But you can't put your recycle in a garbage bag. Then the entire thing is flexible packaging. And then that's just tossed, they don't even look at it. They won't open it and empty it at Rumpke. So this is the Kroger thing, like they have these things when you walk into the store, put the store bags in, and other kinds of plastic can go in there too. And there's some other stuff going on at Kroger. So a lot of the supermarkets are doing this collection stuff. So some things can go in that, some things can't. The things that can't can actually go over to the Cincinnati Recycle Center, like PVC and things, right? So anyway, then there's things that are doing this. This is also a company thing. right? So garbage can, it's got a robot in it with artificial intelligence that you can throw anything in it and it'll figure out, like, so it's got various bins in here. And it sorts the garbage. This is kind of set up for airports and things like that. Anyway, there's more than one company doing this. This is a US company. It's what's it called? TrashBot. Right. So I think this goes to TrashBot if you click it, but it's just basically the same thing, but and just they show it at kind of an airport. This thing is kind of gaining traction, like people see it as a solution to the flexible packaging problem. It's TrashBot, and this is a thing in the, I think it's in Poland or something, this BNE, same thing as TrashBot. Kind of the same idea. I guess they have some people who've signed on to it. So maybe you'll see Benny at the McDonald's somewhere. We go to Europe. This is consumer and this is commercial. So there's companies that are doing recycling of commercial. So this would be like this is when you have a processing plant. So you have if you went to Lyondell, you would have seen this. They have a film line, or it's like an extrusion line for compounding. Then they have the waste, and then they have a vacuum cleaner that pulls up all the waste and sends it over the ceiling and over to the other side, and then it's fed into an extruder that pelletizes it, and it feeds it back into the same machine. Like it's all automated, so that all the scrap. So this is post-commercial, meaning like from the film blowing line. So you can build this right onto your film line. Like you're going to have a thing that just takes the scrap. So when they make the film, the edges aren't the same as the middle, so they trim the edges. So the edge trim is like a big part of the waste. Then when you start it up, you get goo out of it. That's part of the waste. When you shut it down, you kind of get goo. So basically, there's a lot of waste plastic right at the film manufacturing plant. And then you can recycle it. And they're doing it. I mean, they're basically doing that kind of recycling. I think it's a high, 79% post-industrials. Oh, no, that's in landfills. Basically, they're getting a huge fraction of this kind of recycling now. This is old, I think. But anyway, that's just showing the same thing. And then separation. So if you go to the Rumpke tour, you'll see these kind of things. They have all the equipment there. It's in this thing. So this vacuum, like the guys are there, so it'll just suction up the flexible packaging up into a thing that goes somewhere. I'm not sure if there's a video here of these things running. Yeah. So, yes, it's just showing the guys of garbage. This Rumpke looks just like this. Right, they have this kind of vacuum system that Boyd has. That's showing where they go. I mean, they're going to separate further. Oh, and this is one of these extruders. This is a compaction thing, so it compacts it into a tube thing, which is the next. We'll get back there. Oh, just when I finally got.
My name is Nick Davis, and I'm the product development engineer at CP Group.
All right.
We're here to talk about the future of mechanical screening.
Not open anymore.
Bold claim, right? Yes,
Go away there. Thank you. Anyway, let's see, so that's that business, did that. Yeah, maybe this thing I did, let me just make sure, I want to finish this. So, almost out of time. Separation and sorting. All right, so you saw that. Then this is just showing something about how you can, so there's various conveyor belt arrangements where you can pick up the things that are fluffy, then feed them somewhere else. If you go to Rumpke, you'll see these things in operation. The picture doesn't do it justice. And then, I mean, basically a lot of conveyor belts with a lot of these kind of separation things. Air separation, that's blowing the cardboard up or blowing the bags up. And there's these various screening things. So these grab onto the bags, basically. Or you can have a vibration table that separates. Rumpke has all these. I don't think they have a trommel screen like this rotating thing, but they have all these kind of gear things that look like you would fall into and get chewed up. So anyway, this is just the tags. And then there's all the technology, like this, Rumpke has exactly this, like there's an IR beam here. It sees the PET bottles, and then it shoots air, and the bottles go up over a little barrier and pop over. So it collects them all. So it can separate, by IR, it identifies the PET, and it can separate PET from everything else, and it gets all of it, basically. Right, and this thing's flying by, it's not like so static. These things are just going by like a blur, like everything's popping over and it all happens. Right, so that's an IR, that's like a standard tool we're using. Fluorescent identification, you can identify different plastics by using UV lights. It's kind of the same thing as the IR. The IR is like the most standard thing. And this is a robot, they have this at Rumpke. I think this is a video of a robot somewhere else. Rumpke has like a bunch of these same robots. Is it going to get trapped? See, it's just figuring out where the polyethylene jugs are and pulling them out of a mixed stream. So there'll be like 5 of these in a row. So all the bottles get pulled out or whatever it's going after. It gets 100% of it with the 5 of them. Right? It's artificial, like it learns like, it's artificial intelligence. So when it gets it wrong, it gets slapped. When it gets it right, it gets a biscuit, simply. Basically, it learns eventually to get exactly what it's looking for. So anyway, and then this is adding things to separate the aluminum coated from the other things. I don't have a picture of that running, but Rumpke has that too. This is just a table of all the different technologies that they're using for separating things. Basically, IR, the robotic artificial intelligence. I didn't see UV visible there. And then Ramen, I think, is a new thing that they're looking at. But so anyway, there's a lot of technology to separations. And then once you separate, you compact. I showed you that thing in the other film where they feed out the flexible film into some compacted thing. Those are just some tools to do it. And then you can do life cycle analysis on this stuff. Basically, there's some argument to be made that for different types of applications, right, the flexible packaging, even with the waste problem, is better than alternatives in some cases, right? So we can make an argument over it. I think the homework has something about figuring this out, what you think is the best approach to it, Then the end of this, I'm not going to go through now, I think, but basically this is from the MacArthur Foundation website. So if we have time later, I'll go through that. I'll do it now, but that's basically Google, so shut it off. That's basically this other link for this. Packaging, upsize packaging files. Then this MacArthur, I think that's from MacArthur. It's like, this is kind of the other side, like the anti whatever flexible packaging, how you get around it. So you can kind of look through that if you want. It's just a bunch of slides. It's not really a document. They sell this as a book, but basically it's not really a book. It's just a bunch of slides. You know, you can kind of look through that anyone can if you want. Like the homework, why don't I just look at the homework for a second before we go? So we know kind of what we're getting into. Because next time it'll just be Jeff Snyder and I won't have time to look at it, but, explain multilayer films, so problem with. This is kind of like the last part of what are the problems. I can go through that, but basically it's those slides, like in the cards of foundation stuff. What are the steps necessary? So it's like, that's the things I show at the end. And talk about whatever Jeff is gonna talk about. I don't know, the last week was impressive, like you guys did really well on that. So. I hope you do that again, but you don't need to actually, but basically, it was good that you did that. It was really good. So I'm gonna quit there. So I think, I'm going wrong, but any questions or anything on this stuff? Sorry. So, yeah, so next time we'll have them come by. So I'll take attendance next time and stuff. Hopefully everyone shows up. I'll probably advertise it too to get some other people. And like if you have friends that want to hear monkey or whatever, it's good. But, that was